Welcome. Welcome back to the Deep Dive. We're the place you come to really get under the hood of some, well, groundbreaking research.
We try to pull out the key insights, maybe some surprising facts you wouldn't get just from the abstract.
Exactly. And today, we're diving into something pretty fundamental, a question that's really been buzzing in physics for a while now. What if, one of the really core numbers in our picture of the universe, something we thought we knew, what if it just seemed off?
Like a piece of the puzzle suddenly doesn't fit quite right.
Precisely. Imagine that foundational piece, maybe a cornerstone of this huge theoretical structure, just, not fitting. And that's exactly the spot particle physicists were in regarding the mass of the W boson.
That's right. It wasn't just a minor disagreement. For a good while, the community was really wrestling with this significant discrepancy.
Discrepancy in the W boson's mass, specifically.
Yes. There was this extremely precise measurement came out of the CDF Collaboration over at Fermilab's Tevatron.
Right, the Tevatron, before the LHC really got going.
Exactly. And their numbers seemed to, strongly challenge what the standard model predicted. It created this real, almost palpable tension, in how we understood particles, forces, the whole shebang.
You could feel it in the community. Was this a crack in the standard model? That was the big question.
It absolutely was. It wasn't just like academic quibbling. It felt like it could be a potential crack in the bedrock, the very foundation of modern physics.
Okay, and that sets the stage perfectly for why we're so interested in today's deep dive. Because we're going to unpack this incredible technical story behind a brand new measurement.
A high-precision measurement.
Yes, high-precision measurement of that same W boson mass, but this time from the CMS Collaboration.
Over at CERN's Large Hadron Collider, the LHC.
The LHC, exactly. So our mission today isn't just about the final number, though that's obviously crucial. It's about the sheer ingenuity, the cutting-edge science that let them get such amazing accuracy.
How they actually did it.
Right. How did they push the boundaries of experimental precision this far? To really put the standard model to the test, it's a story of, meticulous engineering, super sophisticated theory, massive data analysis.
We're really focusing on the technical wizardry here.
That's the core of it, how they pulled this off.
And what's really fascinating, I think, is looking at how the CMS team tackled the known difficulties. Measuring the W mass is inherently hard.
Notoriously tricky.
Always has been. And they systematically found ways to dramatically cut down the uncertainties that had plagued earlier attempts. A huge factor, you can't overstate this, was the data volume.
The sheer amount of data they had to work with.
Just enormous. They analyzed an event sample that was an order of magnitude larger, 10 times bigger than anything used before for a W mass measurement.
10 times. That alone must make a difference.
It's the foundation. That huge data set was like the canvas they needed for this masterpiece of precision measurement.
Absolutely. So as we go through this, you, the listener, are going to hear about, everything. From calibrating muon detectors with just astonishing precision.
We're talking parts per 100,000 level accuracy.
It's almost unbelievable. Imagine lining up this massive building-sized detector with that kind of microscopic precision. And we'll get into how they used advanced machine learning.
To clean up the data, essentially.
Yeah, refine it. And how they brought in the absolute latest cutting-edge calculations from quantum chromodynamics to interpret what they saw.
It's really a testament to, human ingenuity, isn't it? And just relentless dedication, pushing right up against the frontier of what we know.
So, buckle up. We're about to unpack this really monumental achievement. Let's dive in. Okay, so to really get why this new W boson measurement is such a big deal, technically, we need to quickly sort of paint the picture, set the stage within particle physics.
Right, and at the heart of all this is the standard model.
The standard model, often called our best description of, everything at the smallest scales.
Pretty much. It describes the fundamental particles, the building blocks, and the forces that govern how they interact. It's this framework that's been built up over decades.
Decades of really precise measurements.
Exactly, and it's been stunningly successful. It even predicted particles like the top quark, the Higgs boson, years, sometimes decades, before we actually found them in experiments.
It's kind of the ultimate scientific success story in a way, like a grand periodic table for the most basic bits of matter and energy.
You could think of it like that. It's incredibly robust.
And it relies on these fundamental parameters, right? Like the knobs and dials that define the universe.
That's a good analogy. Things like the masses of the key particles, the W, the Z, the top quark, the Higgs. and also the strength of the fundamental forces, what we call coupling constants.
So why is knowing these numbers, these parameters, with extreme accuracy so vital, especially now?
Well, historically, measuring these things precisely was like a roadmap. It guided the experiments that led to discoveries. Like knowing the likely mass range for the Higgs told physicists where to look, where to focus those huge resources.
Okay, so it helped guide the search.
Right. But today, things are a bit different. We've basically found all the predicted standard model particles, all the parameters in the electroweak sector, that's the unified theory of electromagnetism and the weak force. They're all experimentally constrained now.
So we have values for all the pieces.
We do. And that means precision measurements become an even more powerful tool. They become a test, a really stringent, almost surgical test of the model itself.
So we're not looking for missing pieces anymore. We're checking if the pieces we have fit together perfectly.
Exactly. We're stress testing the whole structure, seeing if any piece, even one that seems to fit, has some tiny imperfection, some slight deviation that might hint at a bigger picture beyond the standard model.
Okay, got it. So let's bring in the stars of today's show, the WIA and the Z bosons.
Right. These are the force carriers for the weak nuclear force.
The weak force, responsible for things like radioactive decay, right? Beta decay.
Yes, beta decay. It allows quarks to change flavor, like a down quark turning into an up quark, or a proton changing into a neutron inside a nucleus. It's fundamental to how elements are formed and decay.
But here's where it gets really, really interesting for our measurement today and really crucial for the standard model. Within the standard model, the masses of these two particles, the W boson mass, MW, and the Z boson mass, MZ, they aren't independent variables, are they?
Not at all. They are locked together, uniquely related to the strengths, those coupling constants of the weak and electromagnetic interactions.
And this relationship isn't just some minor detail.
Oh no, it's a cornerstone, a fundamental pillar holding up the whole standard model framework. It's incredibly predictive.
Incredibly rigid, you said. So what happens if the measured masses, the ones we find in experiments, don't quite match this predicted relationship, even by a tiny bit?
Well, that would be a smoking gun. A clear, unambiguous signal of physics beyond the standard model. BSM physics, we call it.
BSM physics, so new particles, new forces.
Potentially. But here's the subtle part. This BSM physics might not involve new particles that are light enough for us to create directly in our current colliders, like the LHC.
Okay, so how would we see it then?
Through indirect effects. Through subtle quantum loop interactions. Imagine ripples on a pond. New, heavy, unobserved particles could participate in these quantum loops, slightly altering the predicted relationships between the known particles, like MW and MZ.
So even if we can't make the new heavy particles directly, their existence could leave these tiny, subtle fingerprints on the properties of the particles we can measure precisely.
Precisely. You might not see the stone thrown into the pond, but you see the ripples, and those ripples tell you something happened. That's the real why it matters here. Precision measurements like the W mass become a window, a probe, looking for these subtle hints of new physics, even if that physics lies at energy scales far beyond our direct reach.
It tells us the standard model, even with all its success, might just be an approximation of a deeper theory.
It might not be the final word. That's the exciting possibility.
Okay, so we have this elegant, powerful theory. But the real test, as always, is in the lab. What did the W boson mass landscape look like before CMS dropped this new result? What was the experimental picture?
Right. Well, let's start with the Z boson, MZ. For experimentalists, the Z is kind of a dream particle to measure.
Easier to handle.
Much. Its mass has been known with truly exceptional precision for a long time now. The number is 91,188.0 minus 2.0 MeV.
Wow, that's precise.
Yeah.
What's that in relative terms?
It's about 22 parts per million, just incredible accuracy, and that mostly comes from the LEP collider experiments at CERN back in the 90s.
LET, the predecessor to the LAC.
Exactly. LEP was an electron-positron collider, very clean environment. They could do these meticulous scans of the beam energy right across the Z resonance peak. That gave them a really clean, unambiguous measurement of MZ that's basically stood as the gold standard ever since.
So the Z mass was locked down, a perfect benchmark. But the W boson, that was always the difficult sibling, experimentally speaking.
Oh, definitely. Much, much harder to nail down. At LEP, they measured MLW by looking at events where two W bosons were produced simultaneously, W pairs.
Okay, direct reconstruction. Sounds good.
Well, the problem was the rate. The number of W pairs produced was orders of magnitude lower than the number of Z bosons. Just Far fewer events to work with.
Ah, so statistics were a limiting factor.
Hugely. Consequently, the uncertainty on the W mass measurement from LEP was significantly larger, about an order of magnitude larger than for the Z mass.
Okay, what about later measurements at the Tevatron and the LHC itself?
Measurements at Fermilab's Tevatron and early measurements at the LHC improved things, contributing to a world experimental average for milli-W of around 80,369.2 miles nines, 13.3 MeV.
Okay, 13.3 MeV uncertainty. Better than LEP, but still much less precise than the Z.
Exactly. But here's where the tension started brewing. If you took all the other precise electroweak measurements, like the Z mass, the top quark mass, etc., and used the standard model's relationships to predict what the W mass should be.
The global electroweak fit, right?
That's the one. That fit gave a prediction for mil-to-W of 80,353 Bellens 6 MeV.
Hold on, so the prediction, 80,353 to just MeV, was significantly more precise than the experimental average, 80,369 milligauss or 13.3 milli, and slightly different.
Precisely. You see the slight mismatch already. The prediction was tighter, and the experimental average was hovering just a bit higher, though maybe statistically compatible given the larger experimental error bar at the time.
Okay, a hint of tension. But then came the measurement that really blew the lid off thing.
Then came the CDF anomaly. This is really the heart of the puzzle we've been talking about.
CDF at the Tevatron.
Yes.
Yeah.
They performed the most precise single measurement of the W mass before this new CMS result, and they found mel-WW equals 80,433.5 Menius 9.4 MeV.
Whoa, okay, wait. Let's compare that. The standard model prediction was 80,353. The previous experimental average was around 80,369. And CDF finds 80,433, with an uncertainty of just 9.4 MeV.
Exactly. It was way off. It strongly and very surprisingly disagreed with both the standard model prediction and the average of all the other measurements.
How big a disagreement was it with the standard model prediction?
It was about a 7 sigma deviation, 7 standard deviations.
7 sigma. For listeners, that means the probability of this happening just by random chance, a statistical fluke, is astronomically small, like less than 1 in a trillion.
Vanishingly small.
Right.
This wasn't just a slight mismatch, it was a major puzzle. It created this profound tension right in the heart of the standard model. It forced everyone to ask, is the model incomplete? Is this finally the hint of new physics we've been looking for?
Or the alternative?
Or was there some subtle hidden experimental flaw? Some unaccounted for systematic uncertainty buried deep within that single, very complex, very precise CDF measurement?
So the stakes were incredibly high.
Yeah.
Resolving this became urgent.
Absolutely. It made getting an independent measurement with comparable or even better precision from a different experiment utterly crucial. A scientific imperative, really.
Right. Enter CMS at the Large Hadron Collider. Let's talk about the machine and the experiment that delivered this crucial new piece of the puzzle.
Okay. The CMS Collaboration tackled this head-on. They used this absolutely enormous data set collected back in 2016.
From the LHC running at 13 TV proton collisions.
Right. And when we say enormous, they analyzed over 100 million reconstructed W boson decays.
100 million. Oh, just pause on that number.
Yeah.
Compared to previous efforts.
It's an order of magnitude larger, 10 times bigger than any sample used before to measure the W mass.
And that sheer statistical power must be fundamental.
It's absolutely key. It's the bedrock that allows you to beat down the statistical uncertainties to such an unprecedented level. It's like trying to map a coastline. Having vastly more data points gives you a much sharper picture.
Okay, 100 million W bosons. How do you even find them? How do you pick them out from the, chaos of LHC collisions?
Yeah.
What decay channel are they looking for?
They focus specifically on the W boson decaying into a charged lepton, in this case a muon and a neutrino, the WA channel.
Muon plus a neutrino. Why not, say, W decaying into quarks? Those happen too, right?
They do, more often in fact. But quarks immediately turn into messy sprays of particles called jets. And reconstructing the energy of those jets with the kind of pinpoint accuracy needed for a precision W mass measurement is, well, extremely difficult. Maybe impossible right now.
Jets are just too messy. Calibration's too hard.
Exactly. Leptonic decays, on the other hand, especially muons, give you a much cleaner signature in the detector. A single high-energy muon track plus some missing energy from the neutrino. It's inherently cleaner, much more suited for precision work.
Okay, so W to muon neutrino. That makes sense for cleanliness. But the neutrino, that immediately brings up the classic problem, doesn't it?
The neutrino challenge, yes. Neutrinos are famously ghost-like. They barely interact with anything. They zip straight through our detectors without leaving a trace.
So you can't measure them directly?
Nope, not in collider detectors like CMS. And that means you can't fully reconstruct the W boson in the same way you could, say, a Z boson decaying to two muons, where you just add up the energy and momentum of the two visible muons.
Right. So if you can't see the neutrino, how do you infer the W mass?
You have to be clever. You rely on the kinematics, the motion of the particles. You can see the muon, and what you can infer about the invisible neutrino.
How does that work?
Conceptually, think about the W boson at rest before it decays. Its mass gets shared between the muon and the neutrino. Now, in the lab frame, the W itself is usually moving, which complicates things. But crucially, if you look at the momentum transverse to the beam direction.
Perpendicular to the colliding protons.
Exactly. The transverse momentum of the muon, PEA, and the inferred transverse momentum of the neutrino, these distributions have characteristic shapes. Specifically, they show sharp edges or Jacobian peaks, right around half the W boson mass, MW2.
Jacobian peaks, like a cliff edge in the distribution.
Sort of, yeah. Imagine a speed limit sign, there's a sharp cutoff. The Jacobian peak is like that sharp cutoff in the momentum distribution, and the exact position of that peak is directly tied to the W boson's mass.
Ah, okay. So you're not adding pieces up directly. You're looking for the location of the sharp feature in the muon's momentum spectrum. That's the key signature.
That's the core idea, yes. Those peaks hold the information about MW.
But I imagine in the real world of the LHC, it's not quite that simple. There must be complications.
Oh, absolutely. A huge one, especially at the high intensity of the LHC, is pileup.
Pileup. That's when multiple proton collisions happen in the same tiny time window, right? Essentially overlapping events.
Exactly. You might have your interesting W boson event, but happening at the same time, or in nearby beam crossings, are maybe 20, 30, 40 other unrelated proton collisions. All their debris flies into the detector simultaneously.
Like trying to listen to one conversation in a very noisy room.
Good analogy. And this pileup really messes with your ability to measure the neutrino's momentum accurately. Remember, we estimate the neutrino's transverse momentum by looking for missing transverse momentum, PMST basically, adding up everything we do see and seeing what's needed to make it all balance.
Okay.
But pileup adds a lot of extra unwanted energy deposits all over the detector, making it much harder to calculate that PMS accurately. The resolution gets significantly worse with more pileup.
And the 2016 data had a lot of pileup.
More than twice the pileup of any previous WVAS measurement attempt. This was a major challenge. It forced CMS to rethink their strategy. They couldn't rely as heavily on PMS as previous experiments had.
So they had to focus more on the particle they could measure precisely.
Exactly. Put more emphasis on the muon's kinematics, which are less affected by pileup, and develop analysis techniques less sensitive to the PMST resolution. It required a real strategic shift.
And among the leptons, electrons, muons, taus, they specifically went for the muon channel. WA? Why muons?
Muons give the best experimental precision with the CMS detector. Electrons deposit their energy in the calorimeter, which has good but not quite as exquisite resolution for this specific task. Tau leptons decay very quickly into other things, making them much harder to reconstruct cleanly.
But muons.
Muons are special. They're heavy enough that they don't radiate energy easily, and they penetrate through most of the detector material. They travel through the inner tracker, the calorimeters, and into the dedicated muon chambers outside. This long path allows for an incredibly precise measurement of their trajectory, and thus their momentum.
And the CMS detector is particularly good at that.
CMS stands for Compact Muon Solenoid. The name tells you something. It was designed, in part, for excellent muon detection and measurement. It makes the muon channel the natural choice for pushing precision boundaries on the W mass.
Let's talk about that detector then. CMS is this giant, truly monumental piece of engineering. How does its design actually enable these ultra-precise measurements?
It's a masterpiece. It's designed as a multi-purpose, nearly hermetic detector. Hermetic means it's designed to capture, ideally, every single particle emerging from the collision except for neutrinos.
Covering almost all angles.
Right. Its key parts start with the inner tracker. This is made entirely of silicon detectors, pixels, and strips right near the collision point. It's designed to reconstruct the paths, the tracks of charged particles with incredible precision.
That's where the muon track starts.
Yes. Then come the calorimeters, an electromagnetic one made of lead tungstate crystals for electrons and photons, and a hadronic calorimeter made of brass and scintillator for particles like protons and pions. They measure energy deposits.
And all this is inside a magnet.
A huge, very powerful, superconducting solenoid magnet, 3.8 Tesla. This strong field bends the paths of charged particles. The amount of bending tells you their momentum.
More bend means lower momentum.
Exactly. And outside the solenoid magnet, embedded in the massive iron yoke that returns the magnetic flux, are layers and layers of dedicated muon detectors, gas ionization chambers.
So the muons pass through the tracker, the calorimeters, the magnet coil, and then into these outer muon chambers.
Correct, giving multiple measurement points along their path, both in the inner tracker and the outer muon system.
You mentioned the precision of the inner tracker. How good is it for these muons?
It's phenomenal. A typical high-momentum muon track going through the silicon tracker will have at least 12 distinct hits, 12 measurement points, and each of those points is measured with an accuracy of about 15 micrometers in the plane where the particle bends.
15 millionths of a meter.
Yes, about a tenth the width of a human hair. This incredibly fine-grained tracking is where the momentum precision really originates. Because the momentum is derived from the track's curvature, measuring that curvature with exquisite accuracy is absolutely paramount.
Any tiny error in measuring that curve blows up into an error in the momentum and then an error in the W mass.
Directly, it requires just obsessive control over the detector's alignment, calibration, and stability.
Okay, incredible precision. Let's unpack the actual measurement method now, the nitty-gritty. How do they sift through those 100 million candidate events? The data handling, the selection.
Right. The analysis used data collected specifically in 2016, amounting to 16.8 inverse femtobarns of integrated luminosity. They chose this period because the detector, especially the tracker, was performing optimally and very stably.
Got it. Stable conditions are key for precision.
Absolutely. Events were first picked out by the online trigger system, a super-fast computer farm that makes real-time decisions. It required at least one muon with a transverse momentum, PT, over 24 GeV.
A first rough cut.
Yes, and that muon had to be isolated, meaning not too much other energy nearby, and meet certain quality criteria. This initial trigger selection was carefully designed to be consistent between the W analysis and the Z analysis, which is crucial for the validation later.
Consistency across the board. Okay, so after the trigger, what were the tighter selection criteria for the W and events that made it into the final analysis?
They required the muon to be within the central part of the detector, specifically its pseudo-rapidity, had to be less than 2.4.
Pseudo-rapidity. That's basically the angle relative to the beam.
Essentially, yes. W2.4 keeps the muon within the well-instrumented barrel and end cap regions of the tracker, avoiding the very forward regions where measurements are trickier. And its transverse momentum, BOM-ET, had to be in a specific range between 26 and 56 GeV.
Why that specific momentum range?
That range contains the Jacobian peak region, where the distribution is most sensitive to the W mass. Going too low brings in more background. Going too high loses statistics and sensitivity. It's an optimized window. And of course, the muon had to pass very stringent quality checks on its track reconstruction and be well isolated.
Cleaning up the sample as much as possible. But even then, you still have backgrounds mimicking the signal. How do they tackle those? That's always a huge challenge.
It is. Background rejection was a major focus. Beyond the isolation and track quality, they used some pretty sophisticated techniques. One key thing was using machine learning.
ML comes in.
How? They used ML algorithms specifically to improve the resolution of the missing transverse momentum, a MISTI. Even though they couldn't rely on it as heavily as past experiments, improving its measurements still helped.
How does better MISTI resolution help?
A sharper PMIST measurement leads to a sharper measurement of the W boson's transverse mass, MWT. This is a quantity calculated using the muons, PT, and the PMIST. For genuine W events, this distribution gets narrower, making it easier to separate the signal from backgrounds which tend to have a broader MWT shape.
Okay, so ML sharpens the picture, improving signal background separation. Clever.
Very effective. They also applied hard cuts, like requiring MWT to be above 40 GeV, which cuts out a lot of low-mass background, and they vetoed events if they saw any electrons with PT10 GeV or any additional muons with PT15 GeV to reject Z-boson decays and other processes.
Right, ensuring it really looks like just one muon and missing energy.
Exactly. After all this, they ended up with that sample of 117 million events, and they estimated the fraction that were actually WA was about 89%. Which is remarkably high for a hadron collider measurement.
117 million events, 89% pure, that's the core data set. But they didn't just analyze Ws. They used Z-bosons as a crucial control sample, right? As a way to validate everything.
Absolutely essential. They used two different Z-boson samples. First, the standard ZO sample decaying to 2 muons. They collected about 7.5 million of these.
Both muons detected.
Yes. They required the muons to have opposite charge, and their combined invariant mass had to be between 60 and 120 GeV, centered around the known Z mass. This sample was incredibly pure, over 99.5% Z bosons.
So a super clean sample to check basic things like muon reconstruction efficiency and momentum scale.
Exactly. It's the gold standard for checking the detector's core performance for muons.
Okay, that's the first Z sample. What was the second, the W-like one? That sounds intriguing.
This was the really clever one, designed specifically to mimic the W measurement conditions. They took Z events, but then they deliberately ignored one of the muons.
Threw away information.
Essentially, yes. They treated the second muon as if it were an invisible neutrino. They analyzed the event using only the kinematics of the first muon and the inferred missing momentum, which in this case they knew should correspond to the second muon.
Wow. So they made the Z analysis artificially harder, mimicking the W analysis where the neutrino is genuinely invisible.
Precisely. They even applied similar kinematic cuts, like requiring the transverse mass calculated this way to be above 45 GeV. And they split the sample to ensure statistical independence. This W-like Z analysis was absolutely critical. It allowed them to test their entire analysis chain, including the complex fitting procedures and theoretical modeling, on a system where the underlying mass, mz, was known to very high precision.
It's like running a full dress rehearsal with a known script before the actual performance with the unknown W mass.
That's a perfect analogy.
Yeah.
If their method couldn't recover the known Z mass correctly in this W-like scenario, they'd know something was wrong before they even looked at the W data.
Okay, makes total sense. And underpinning all of this, the analysis, the background estimation, understanding the detector, were massive computer simulations, Monte Carlo.
Indispensable. They generated truly vast Monte Carlo samples, 4 billion simulated W boson events, 400 million simulated Z boson events.
4 billion. The scale is just staggering.
It has to be, to match the precision of the data. And these weren't simple simulations. They used state-of-the-art generators. Min-low PS for the core particle production, which gives very high theoretical precision. P-Lite IA for the complex process of parton showering and hadronization, how quarks and gluons turn into the particles we actually see. And photos plus to handle final state photon radiation, which is another important precision effect.
So incredibly detailed simulations trying to capture all the physics.
Yes. They are absolutely vital for understanding the detector's response in minute detail, for estimating the size and shape of various background contributions, and ultimately for comparing the real data to the theoretical predictions to extract the W mass. The simulation is the template against which you measure the data.
But simulations are only as good as their inputs and how well they reflect reality. How do they account for real-world effects like that pileup issue or the fact that detectors aren't perfectly efficient?
Great question. They didn't just use the raw simulations, they meticulously corrected them. For instance, the distribution of pileup and the exact location of the primary collision vertex in the simulation were adjusted or reweighted to perfectly match what was observed in the actual data.
So the simulation environment mirrored the real data environment.
As closely as humanly possible. And detector efficiencies weren't just taken from the simulation either. They measured the efficiencies for triggering, reconstructing, identifying, and isolating muons directly from the data itself.
Oh.
Using that clean Z sample and a technique called tag and probe.
Tag and probe. Sounds like a spy game.
Maybe a bit. The idea is simple but powerful. You find a Z event. You take one muon that passes very tight criteria, that's your tag. You know it's definitely a good muon from a Z decay. Then you look for the other muon from the same decay, that's your probe. You see how often your standard selection criteria manage to find that probe muon.
So you use the Z decay itself to calibrate how well you find muons.
Exactly. By doing this millions of times, you build up a very precise, data-driven map of your detector's efficiency across different momentum ranges and detector regions, independent of the simulation's initial assumptions. It's a cornerstone of precision measurements at colliders.
Very clever. Okay, and what about the main background processes they had to subtract? What were the biggest contaminants in that 89% pure W sample?
The dominant backgrounds were twofold. First, non-prompt muons. These aren't directly from the W decay, but come from the later decays of heavy quarks, like bottom or charm hadrons, produced in the collision.
So real muons, but not the signal muons.
Correct.
Yeah.
The second main background was actually from Z-air decays, where one of the two muons wasn't detected for some reason. Maybe it went outside the detector acceptance or failed reconstruction. This mimics the W signature of one muon plus missing energy.
Okay, those sound like the main culprits. How do they estimate and subtract them?
The non-prompt muon background, the biggest one, was estimated using data-driven techniques, specifically something called the extended ABCD method. This involves defining sideband regions in the data regions where you expect mostly background and very little signal, for instance, by looking at muons that are not well isolated. By studying these sidebands, you can model the shape and normalization of the background and subtract it from the signal region.
Using the data itself to model the background.
Wherever possible, yes. They did apply a small correction factor based on simulation, but the bulk of the estimate was data-driven. The total uncertainty they assigned to this background subtraction was about 3.2 MeV on the final W mass. They also had to carefully calibrate the hadronic recoil.
Hadronic recoil, what's that?
It's basically everything else produced in the collision apart from the muon and neutrino, all the jets and soft particles. These particles recoil against the W boson, and how well you measure them affects how well you measure the missing momentum.
Ah, because pimicity is the imbalance of everything you do see.
Precisely. So they used ZE events, where there's ideally no real missing momentum, to calibrate the response of the detector to this hadronic recoil. This improved the modeling of the MISTI and the transverse mass, ensuring corrections were accurate to better than 1%. It's another example of using the Z boson to fine-tune the understanding needed for the W.
It sounds like almost every step involved cross-checking and calibrating with Z bosons.
It's the anchor for the whole measurement.
Okay, this is incredibly detailed. Now let's get to what the source material flags as the absolute biggest single source of uncertainty, the muon momentum calibration.
All right.
Why is this so critical and so hard? And what did CMS do to push the precision here?
This really is the absolute linchpin, the experimental backbone. Think about it. If you mismeasure the muon's momentum scale, say you think it's 1% higher than it really is, that error translates almost directly, 1-to-1, into an error on the W mass.
So a tiny calibration error gets magnified.
Exactly. Achieving the required precision means understanding, at an almost unbelievably detailed level, everything that can affect how a muon's track is measured as it flies through the detector.
Like what specifically?
Okay, imagine. The precise alignment of every single silicon sensor relative to every other sensor, down to micrometers, across this enormous detector. The exact strength and uniformity of that huge magnetic field everywhere the muon travels, and the precise amount and type of material the muon passes through every bit of silicon, support structure, cooling pipes, cables, because that affects its energy loss and causes tiny deflections from multiple scattering.
Every tiny detail matters. Getting any of that slightly wrong introduces a bias.
A systematic bias. It's an immense challenge in calibration and alignment.
So how did CMS tackle this Herculean task?
They employed several key strategies. First, and this is crucial, the definitive momentum measurement relied exclusively on the silicon inner tracker.
Not the outer muon chambers, even though it's the muon solenoid.
The outer muon system was vital for identifying muons and for triggering, but the ultimate track fit for momentum used only the ultra-precise hits in the silicon tracker. They used a sophisticated track-fitting algorithm called a continuous variable helix, CVH fit.
CVH fit.
Think of it as tracing the muon's curved path, but continuously accounting for how its momentum changes slightly as it loses energy passing through material, and how it gets nudged slightly off course by multiple small scatters. It's a more accurate way to reconstruct the trajectory than simpler helix fits.
Okay, so better tracking algorithms. What else?
They used a super detailed 3D map of the magnetic field, going beyond the standard model used for many other CMS analyses, aiming for higher accuracy. And they performed an extended, incredibly complex alignment procedure for the tracker components, incorporating fine-grained corrections that accounted for local variations in the magnetic field and the material budget.
Alignment is key. How do you know you've got it right? How do you set the absolute scale?
That's where known particles come in. The primary calibration relied on the Judd resonance. The Just Boson decays to 2 muons, and its mass is known extremely precisely from other experiments.
Like a standard candle or a standard ruler inside the detector?
Exactly. By reconstructing millions of Jeffian decays and demanding that their calculated invariant mass match the known Jeff mass, they could derive fine-grained corrections to the muon momentum scale. These corrections were parameterized as a function of the muon's pseudo-rapidity, essentially mapping out tiny imperfections across the detector.
So they used JETCH to fix the scale across different detector regions?
Yes, and then they had to extrapolate these corrections from the typical momentum of muons from jet decays, relatively low, up to the momentum range relevant for W decays, much higher. This extrapolation used a physics-based model to account for expected momentum dependencies.
And how did they check if this JETCH calibration and extrapolation actually worked reliably?
Validation, validation, validation. They checked it rigorously using other known resonances, the Olin-S meson, which also decays to but at a higher mass than J, and of course the Z boson itself decaying to Heim. They applied the J-derived corrections to muons from these decays and checked that they reconstructed the correct Ol and Z masses. Consistency across all these different mass scales gave them confidence in the calibration.
Okay, that's the momentum scale. What about the momentum resolution? How precisely they can measure the momentum, not just the average value?
Good point. That's also critical. The resolution is affected by things like multiple scattering, which depends on momentum. They had to ensure the resolution in their simulation matched the resolution in the real data precisely. Again, they used both J and Z events to derive corrections for the simulated resolution, making sure it accurately reflected reality. The uncertainty assigned to this specific resolution correction was about 1.4 MeV on the W mass.
It's just layer upon layer of meticulous correction and validation.
That's precision measurement.
So, after all that intense effort on the muon momentum, what was the final uncertainty contribution from this source? How much did they manage to limit it to?
The final uncertainty on MW from the muon momentum scale calibration was 4.8 MeV.
4.8 MeV, so still the single largest experimental uncertainty.
Yes. It highlights just how incredibly challenging this aspect is. Getting below the 5 MeV level is already a monumental achievement, requiring truly state-of-the-art understanding and control of the detector. It's roughly a 60 parts per million uncertainty contribution. This is where the experimental wizardry really shines.
Okay, absolutely critical. But experimental effects are only half the story. You also need incredibly precise theoretical predictions to compare the data to. Let's dive into the theoretical corrections and uncertainties.
Right. You can have the world's best measurement, but if your theoretical template is flawed, you'll get the wrong answer. CMS collaborated closely with theorists to use the most advanced predictions available.
How advanced are we talking?
The predictions for the key distributions, like the muon pointee spectrum, were calculated at what's called N3LL plus NNLO accuracy in perturbative QCD.
N3LO plus NLO. Okay, break that down. Sounds like alphabet soup.
Huh. It is a bit. Think of perturbative calculations like an expansion series. Leading order, LO, is the first rough estimate. Next to leading order, NLO, adds the first set of corrections. Next to leading order, NNLO, adds the next set. Going to NNLO is already extremely complex and computationally intensive.
Okay, so NLO is very high precision fixed order calculation. What's the N3LO part?
That refers to logarithmic resumation. At the edges of phase space, like the Jacobian peak region, certain types of quantum corrections become large and need to be summed up, resummed to all orders in perturbation theory. N3LL means next to leading logarithmic accuracy. Combining NNLO fixed order with N3LL resumation gives you the current state-of-the-art prediction for these processes.
Wow, so pushing theoretical calculations to their absolute limit.
Absolutely. Decades of theoretical development and immense computing power are needed to get there.
But even with N3LL plus NNLO, there are still theoretical uncertainties, right? What are the main ones they had to grapple with?
Yes, even at this level, uncertainties remain. One of the biggest comes from the Parton distribution functions, the PDFs.
PDFs again. Remind us what those are.
They describe how the momentum of the colliding proton is shared amongst its constituent quarks and gluons. We don't know these perfectly. They have to be extracted from experimental data, and that process has inherent uncertainties.
And why are they so important for the W mass?
Because the PDFs determine exactly which quarks and antiquarks inside the protons are most likely to collide and produce the W boson. This affects the W's production rate, its average momentum along the beamline, and even its polarization, its spin state, all of which influence the kinematics of the decay muon we actually measure.
So uncertainty in the proton structure directly translates to uncertainty in the W prediction.
Directly. PDF uncertainty was actually the second largest source of uncertainty in the final CMS result, right after the muon momentum scale. They used a modern PDF set called CT18Z for their main analysis.
Okay, PDFs are one major source. What else?
There are uncertainties from missing higher order corrections. Even N3LL plus NNLO isn't the absolute final answer. There are still N4LL terms, N3LO terms, etc. that haven't been calculated yet. You have to estimate the potential size of these missing pieces.
So uncertainty from the unknown unknowns in the theory.
In a way, yes. And then there are non-perturbative effects. These are related to the complex, long-distance dynamics inside the proton that can't be calculated with standard perturbation theory. Things like the intrinsic transverse jiggle of the partons before they collide. This impacts the W boson's own transverse momentum distribution, PWT, especially at low values.
Okay, so these inherent theoretical limitations exist. Now, CMS did something really novel regarding that W transverse momentum, PWT, didn't they? They didn't just rely on theoretical predictions or Z boson data.
This was a truly significant innovation in their analysis. Historically, hadron collider W mass measurements often relied heavily on measurements of the Z boson's transverse momentum, PZT, to model the W's transverse momentum, PWT. They assumed the physics governing PWT and PZT was very similar and used the cleaner Z data to constrain the harder-to-predict W distribution.
Makes sense, but it relies on an assumption about the WZ correlation.
Exactly. And that assumption itself carries uncertainty. CMS took a different approach. They built their analysis around a multidimensional fit. They binned their WEA data very finely in 3 variables: the muon's transverse momentum, PEDT, its pseudorapidity, and its charge.
Okay, a 3D picture of the data.
Yes, and then they performed a maximum likelihood fit using theoretical templates for these distributions to extract mil-GW. But here's the key innovation. The parameters describing the WASON's transverse momentum spectrum, PWT, were included as free parameters in the fit to the W data itself.
Wait, so they didn't assume the PWT shape from Z data or theory? They let the W data itself determine the best PWT shape simultaneously with measuring the W mass.
Precisely. This is what they mean by constraining PWT in situ. The W data itself told them what the PWT distribution looked like. This dramatically reduced the reliance on the Z data and the associated WZ correlation uncertainties. It also had the powerful side effect of helping to constrain the PDF uncertainty simultaneously because the PWT shape is sensitive to PDFs.
That sounds like a major breakthrough, turning a source of uncertainty into something constrained by the measurement itself.
It's a huge step forward in robustness. It makes the result less dependent on external inputs and theoretical assumptions about PWT. A really elegant analysis technique, leveraging their huge data set.
Okay, very clever. They also introduced something called theory nuisance parameters, or TNPs. What are those about? Sounds technical.
It is technical, but it's about handling those theoretical uncertainties we mentioned in a more sophisticated way. Specifically, the uncertainties from missing higher order corrections. The TNP approach, developed within a framework called soft collinear effective theory, SCET, tries to parameterize the impact of these unknown corrections based on the known structure of the theoretical calculations.
So instead of just assigning a single overall uncertainty number, it tries to model how the uncertainty might affect different parts of the calculation.
Kind of. It introduces parameters, TMPs, associated with different parts of the calculation, like hard scattering, parton evolution inside the proton beams, soft radiation, and quantifies the uncertainty based on the expected size of the next uncalculated terms. It provides a more structured way to estimate the theory error and its correlations across different kinematic regions, and even with the W mass itself.
A more rigorous way to put error bars on the theory predictions.
Exactly. Crucial when you're aiming for this level of precision, where small theoretical effects matter, and traditional uncertainty estimates might be too simplistic or even underestimate the true error.
Makes sense. And I read they also had a completely different alternative analysis method as a cross-check based on angular distributions, a helicity fit.
Yes, they did. This was another important robustness check. In this alternative analysis, they didn't just fit for MW. They simultaneously fitted for parameters describing the angular distribution of the muon from the W decay.
How does that help?
The angular distribution depends on the W boson's spin state, or helicity. The standard model makes specific predictions for these helicity states. This alternative fit uses a general parameterization that allows these helicity components, there are 9 of them for a vector boson like the W, to vary. Each component predicts a slightly different shape in the muon's pointy end distribution.
So it lets the data determine the W's spin properties at the same time as its mass.
Right. Now, doing this actually reduces the sensitivity to milliWs slightly. The uncertainty on LW from this fit is larger, but its value lies in being less dependent on the specific theoretical predictions for W production and polarization. By relaxing those assumptions and letting the data determine the angular structure, it provides a powerful, independent cross-check that the primary measurement isn't being biased by subtle inaccuracies in the standard model production model they used.
So a less precise but potentially more assumption-free check, like
Yeah.
solving the same problem with a different method.
Exactly. Finding consistency between the two methods significantly boosts confidence in the final result.
Okay. And finally, on the theory side, just quickly, electroweak corrections, things like photons being radiated.
Yes, those were included too. Things like final state radiation, FSR, where the muon emits a photon after the decay, initial state radiation, ISR, from the incoming quarks, and virtual electroweak loop corrections. These are generally smaller effects for the W mass measurement. FSR's impact was estimated at less than 0.3 MeV uncertainty. The virtual electroweak corrections contributed about 1.9 MeV small compared to the muon scale or PDFs, but definitely need to be included when you're aiming for 10 MeV total precision. Every bit counts.
Okay, so we have the data meticulously selected, the detector calibrated to the nth degree, the theory predictions refined to state-of-the-art. How do you put it all together? What's the statistical machinery that spits out the final number and its uncertainty?
The core of it is a sophisticated statistical fit specifically, a binned maximum likelihood fit. They take that 3D distribution of the data, PT, ET, AQ, divided into thousands of bins.
Thousands. How many exactly?
Around 3,000 bins in total. And they compare the number of events observed in each bin to the number predicted by their theoretical model, the sum of the W signal simulation plus all the estimated background contributions.
Okay, comparing data to prediction bin by bin.
Right. But the theoretical prediction isn't fixed. It depends on the W mass itself, of course, but also on all those sources of systematic uncertainty. We discussed the muon momentum scale, the PDFs, the theory uncertainties, the background estimations, detector efficiencies.
So all those uncertainties go into the fit.
Yes, as nuisance parameters. Each source of uncertainty is represented by a parameter in the fit that's allowed to vary around its central estimate, usually constrained by a Gaussian distribution representing its estimated uncertainty size, like the 4.8 MeV for muon scale.
So the fit finds the W mass value that best describes the data, while simultaneously allowing all these systematic uncertainties to fluctuate within their reasonable ranges.
Exactly. And crucially, the fit can actually constrain some of these nuisance parameters. If varying a particular systematic uncertainty makes the prediction fit the data much worse, the fit will tend to pull that parameter back towards its central value or even reduce its effective uncertainty. It's called profiling. The data itself helps refine the impact of the systematics.
So the fit isn't just finding MW, it's finding the best combination of MW and all the systematic parameters that explains the data.
Precisely. And they carefully model the correlations between uncertainties, for instance, how a shift in the muon momentum scale affects different bins, or how a particular PDF uncertainty impacts both W plus and W predictions. This is vital for getting the final uncertainty right.
That sounds computationally monstrous.
Yeah.
3,000 bins, and how many nuisance parameters?
Around 4,000 nuisance parameters in total. It's an enormous computational undertaking.
How is that even feasible?
It pushes the boundaries. It was made feasible by using modern computing tools, specifically the TensorFlow software package, which is often associated with machine learning.
TensorFlow, for a physics fit.
Yes. Its ability to handle large-scale optimization problems and perform automatic differentiation, which is needed to calculate how the prediction changes as you vary all those parameters, makes it incredibly powerful for these complex physics fits. It allows them to run the millions of iterations needed to find the best fit point and accurately map out the likelihood function to determine the uncertainties. Without tools like this, managing a fit of this scale would be practically impossible.
So, cutting-edge computational science, enabling cutting-edge particle physics.
Absolutely intertwined.
Now, something else I found fascinating about their methodology, really speaking to scientific rigor, data blinding.
Yeah.
Can you explain what that is and why it was so important here, especially given the history with the CDF result?
Blinding is a crucial procedure in precision measurements, designed specifically to prevent unintentional experimenter bias. The basic idea is to hide the actual result from the analyzers until the entire analysis procedure is finalized.
How did they do it here?
For the CMSW mass analysis, the entire pipeline, data selection, calibration, background estimation, the fitting code, everything was developed and optimized using only the simulated Monte Carlo samples. While they were doing all this development work, a secret random offset was deliberately added to the value of MW and MZ in the control analyses that their analysis code would output.
So the physicists doing the work literally didn't know the answer their analysis was giving.
Exactly. They knew the offset was somewhere between medical 500 and plus 500 MeV, a huge range, but they didn't know the specific value. They had to finalize every single choice, every cut, every correction, every systematic uncertainty evaluation based only on internal consistency checks, simulation studies, and the Z boson validation analyses without knowing where the W mass value was actually landing.
Only when everything was locked down, reviewed, and approved.
Only then was the secret offset removed, the analysis run one final time on the actual data, and the true result revealed. Unblinding, they call it.
Why go to such lengths? What kinds of subtle biases could creep in if they weren't blinded, especially with the shadow of the CDF anomaly looming?
It's about protecting against unconscious confirmation bias. Imagine you're analyzing the data, and you see a preliminary result that looks very close to the standard model prediction, or maybe very close to the CDF result. Subconsciously, you might be tempted to stop scrutinizing certain aspects, or maybe you'd question a particular systematic uncertainty more if it pulled the result away from where you expected it to be.
You might inadvertently tune the analysis towards a preconceived notion.
Precisely, even with the best intentions. Blinding forces the entire collaboration to agree on a procedure that is objectively robust and well justified based on its performance in simulations and control samples, completely independent of what the final W mass number turns out to be. It ensures the methodology is sound before the high-stakes answer is known.
It isolates the scientific process from human psychology in a way.
It's a powerful safeguard for objectivity, especially when the result has potentially profound implications, like confirming or refuting a previous anomaly. It ensures the data gets the last word unbiased.
Okay, essential for credibility. Let's move to that crucial validation phase. They used the Z boson as their ultimate benchmark. How did that work in practice? How do they use the known Z mass to prove their method was sound?
The Z boson is the perfect tool for this. As we said, its mass is known incredibly precisely from LEP. It decays cleanly to 2 muons, so you can see all the decay products. And its production mechanism at the LHC is very similar to the W's, meaning they share many of the same experimental challenges and theoretical uncertainties.
So it's like a W boson, but with the answers already in the back of the book.
Pretty much. If your analysis machinery, your detector calibration, your understanding of backgrounds and theory can't accurately reproduce the known Z mass, you have no business claiming you can measure the W mass precisely.
Makes sense. So they did 2 specific Z mass measurements for validation.
Correct. 2 complementary checks. The first was a straightforward direct measurement of MZ using the standard Z decays, reconstructing the invariant mass of the 2 muons.
The clean channel. What did they find?
They performed a maximum likelihood fit to the dimuon mass distribution. Their result, when compared to the official world average Z mass, MPDGZ, equals 91,188.0 minus 2.8 MeV, showed a difference of just minus 2.2 minus 4.8 MeV.
Minus 2.2 plus or minus 4.8 MeV.
Yeah.
Perfectly consistent with 0 difference. Excellent agreement.
Absolutely spot on. It demonstrated that their fundamental muon reconstruction and momentum scale calibration were working beautifully for this clean, fully reconstructed decay.
And interestingly, they use these Z-wing events not to set the muon momentum calibration, but to determine its uncertainties. So this agreement is a non-trivial check of that whole process.
Exactly. It validates that their estimated systematic uncertainties on the muon scale were realistic and captured any potential residual miscalibrations. It's a closure test.
Okay, that's the first check. What about the second, arguably even more critical one, the W-like Z measurement?
This was the real stress test, mimicking the W analysis as closely as possible. Remember, they took ZO events but pretended one muon was a neutrino, using only the other muon and the missing momentum. They then ran their full W mass analysis machinery, the 3D binned likelihood fit to, PTQ, on this W-like Z sample.
Applying the exact same complex procedure used for the W, but to this artificially constructed Z sample where they knew the underlying mass, that's gutsy.
It is, but it's the ultimate validation, the result. They measured an MZ value that differed from the known world average by -6 a 9 of 14 MeV.
-6 plus or minus 14 MeV. Again, perfectly consistent with 0 difference, well within the uncertainty.
Yes. Considering the added complexity and the deliberate discarding of information, this level of agreement was a massive success. It showed that their entire analysis framework, including the sophisticated theoretical templates from CElib plus DY Turbo, and the procedure for handling nuisance parameters, could correctly extract the known mass even under these challenging W-like conditions.
And crucially, it validated their novel approach of constraining the transverse momentum, PWT or PZT, in situ from the Lepton kinematics.
Absolutely. The fact that the W-like-Z analysis gave the right answer confirmed that the Pepose distributions really do contain enough information to constrain the boson's transverse momentum modeling directly from the data without relying on external assumptions.
This was huge, right? Because it meant they could apply the same technique to the W data with confidence.
Tremendous confidence. It validated their ability to make the W mass measurement largely independent of assumptions about how W and Z boson transverse momenta might be correlated, a major systematic uncertainty that had plagued previous measurements. This independence, demonstrated through the W-like-Z analysis, is one of the key strengths and improvements of the CMS result.
Okay, the stage is fully set. Meticulous preparation, cutting-edge techniques, rigorous validation. It's time. After all that, after unblinding, what was the final W boson mass measured by CMS, the number everyone was waiting for?
The final result from the CMS collaboration is MW equals 80,360.2 more against 2.4 statistical uncertainty, and again 9.6 systematic uncertainty.
Combining those uncertainties in quadrature.
Gives a total uncertainty of 9.9 MeV. So the final number, 80,360.2 MeV, is 9.9 MeV.
80,360.2 menis and 9.9 MeV.
Okay, now the crucial comparison. How does this number stack up against the standard model prediction and, importantly, against that anomalous CDF result? Has the puzzle been solved?
Let's compare. The standard model prediction from the global electroweak fit is around 80,353 meni a 6 inter MeV. The CMS result of 80,360.2 meni on a 6 MeV is an excellent agreement with that prediction. It's comfortably right where the standard model expects it to be.
Wow. Okay. So agreement with the standard model.
Yes, a monumental finding. Now compare it to the CDF result. 80,433.5 NNA and 9.4 MeV. The CMS value is clearly significantly lower than the CDS value. They are in disagreement.
So the tension is resolved, but in favor of the standard model. That's exactly what this result indicates. CMS, with a precision comparable to CDF's, using a completely different collider, detenter, and analysis techniques, finds a value perfectly consistent with the standard model prediction and inconsistent with the CDF anomaly.
Which strongly suggests.
It strongly suggests that the CDF result, while incredibly precise for its time, likely suffered from some unaccounted for systematic uncertainty, or perhaps an extremely unlikely statistical fluctuation. The CMS result basically brings the W mass measurement back into line with the standard model picture.
That's huge. It alleviates that major tension that had the particle physics world buzzing for years.
It really does. It's a powerful affirmation of the standard model's predictive power and robustness, showing it withstands even these incredibly stringent tests at the precision frontier.
Let's quickly revisit the uncertainties in the CMS result. Even with their amazing work, where did the biggest remaining uncertainties come from?
As we discussed, the two dominant sources were the experimental uncertainty from the muon momentum scale calibration, contributing 4.8 MeV, and the theoretical uncertainty from the Parton distribution functions, contributing 4.4 MeV.
So nailing down the detector calibration and understanding the proton's guts remain the key challenges for pushing precision even further.
Absolutely. Those are the frontiers. But it's also crucial to remember how well CMS managed other systematics. Their novel techniques for constraining the W boson production uncertainties, like PWT, in situ directly from the data, successfully made those uncertainties subdominant. That itself was a major technical victory.
How does the CMS result compare in precision to other measurements, besides CDF, like from ATLS at the LHC or D0 at the Tevatron or LEP?
The CMS result is significantly more precise than all other measurements performed at the LHC so far, by ATLA or LHCb. It's also more precise than the earlier Tevatron measurements from D0. Its precision is comparable to the CDF result, which was the previous single most precise measurement. So CMS now provides the new benchmark measurement, strongly anchored by its agreement with the standard model.
Got it. They also did one more interesting check, didn't they? Measuring the mass difference between the positively charged W plus and the negatively charged W boson. Why do that?
That's a test of a fundamental symmetry called CPT invariance. CPT symmetry predicts that particles and their antiparticles should have exactly the same mass. The standard model strictly adheres to CPT, so it predicts MW plus should be identical to MW. Measuring the difference is a way to check for tiny violations of this principle, or perhaps subtle charge-dependent effects in the detector or analysis.
A consistency check of fundamental principles. What did they find for the difference?
They measured MW plus MWS equals 57.0 menis, 30.3 MeV.
Okay, 57 MeV difference, but with a large uncertainty of 30 MeV. Why is the uncertainty on the difference so much larger than the uncertainty on the average mass, which was 9.9 MeV?
Because many of the largest systematic uncertainties largely cancel out when you take the average of W plus and W, like aspects of the PDF uncertainty or common calibration factors. But when you take the difference, uncertainties that affect W plus and W differently become dominant.
Like what?
Things like potential charge-dependent biases in the muon momentum measurement, maybe positive muons are measured slightly differently than negative ones, or differences in the theoretical predictions for W plus versus W production related to quark versus anti-quark PDFs and their angular distributions. These charge-specific systematics add up in the difference, leading to the larger uncertainty.
So the measured difference of 57 megalite MeV, statistically, it's maybe 2 sigma away from zero. A slight hint, but not significant.
Exactly. Given the large uncertainty, it's perfectly consistent with zero, as expected from CPT symmetry. It mostly serves to highlight the incredible challenge of controlling charge-dependent systematic effects at this level of precision.
Okay, so summing it all up, this CMS result isn't just another data point. What's its overall significance for particle physics moving forward?
It's truly a landmark achievement. It represents a major step towards measuring the W mass with an experimental precision that rivals the precision of the standard model prediction itself. It showcases the phenomenal capabilities of the CMS detector and the LHC for precision physics. And perhaps most importantly right now, by resolving the tension created by the CDF result in favor of the standard model, it powerfully reaffirms the model's validity and predictive power at the highest energies and precision scales we can currently probe. It's a triumph for the standard model and for experimental ingenuity.
And there you have it. We've taken a really deep dive today into the remarkable story of how the CMS collaboration measured the W boson mass with unprecedented precision.
It's a story combining massive data sets, incredibly sophisticated detector calibration, cutting-edge theoretical calculations, and innovative analysis techniques.
All coming together to provide a crucial answer to a puzzle that had lingered for years. The result, a powerful confirmation of the standard model.
That agreement, especially after the CDF anomaly had raised so many questions, really underscores just how robust our current understanding of fundamental particles and forces actually is. The standard model just keeps passing these incredibly stringent tests.
But, as always in science, even as we confirm current theories, the quest for what lies beyond continues. This result strongly supports the standard model, yes, but the search for new physics never stops. It just refines where we look.
Exactly. And it prompts the question, what's next for precision? What new experimental innovations, maybe in detector technology or analysis techniques, will be needed to push the W mass precision even further? Could we reach a level where even smaller discrepancies might emerge, hinting at those subtle effects of new physics?
Maybe future detector upgrades, even more powerful simulation and theoretical tools, or perhaps new ways to leverage machine learning to squeeze even more information out of the data. What might the next frontier look like in refining these fundamental parameters?
It'll likely be a combination of all of the above. Pushing detector resolution further, improving our understanding of PDFs through new measurements, calculating theoretical predictions to even higher orders, developing smarter algorithms. It's a continuous, synergistic effort on all fronts to probe deeper into the fundamental structure of the universe.
A fascinating prospect. The journey of discovery certainly continues. To stay updated on the latest research papers, including those at the intersection of physics, AI, and ML, definitely visit our webpage. The link is in the bio.
Thanks for joining us on this deep dive.
Yes, thank you for tuning in as we explored the heart of particle physics precision.